Yeah, thank you very much again for having me. The title is Seeing Through Forest, and the German subtitle that you can see here is Sehe, was du nicht siehst. The English translation would be I spy through my little eye. That was the title of an article in the German Drones magazine that featured our work about 1.5 years ago. And before I go into a bit more details on what we actually are doing, I would like to show you a video that FLIR, which is one of the major companies for thermal imaging systems, did after our Nature publication in November, which summarizes our work pretty well. Airborne optical sectioning is a synthetic aperture imaging technique that allows to remove occlusion of dense vegetation using aerial systems such as drones. And we apply it in different fields such as search and rescue, wildlife observation, archaeology, and also recently for people tracking through dense foliage. So this is very recent results. We just submitted the paper on Friday. What you can see here is an aerial video that is recorded by a drone in forest or over forest. And I'm not sure if you can spot him, but there should be a person walking underneath the tree crowns. So it's because of the heavy occlusion, you will not see much of him. If we apply very simple tracking, which in this case is a combination of color anomaly detection, plop detection, and Kalman filtering, you will see that basically you end up with lots of garbage. You will detect a lot of false positives, certainly not being able to detect the person at all and not to track him at all. So with airborne optical sectioning, we can remove the occlusion with the same data. So this is the results of airborne optical sectioning with the same image footage that you have seen before. We remove occlusion and are very well able to detect two targets in this case. The larger target is actually a static light source on the ground, which we placed on the ground just for spatial reference. And the smaller target is actually the person that is being detected here and can also be pretty reliably being tracked. So this is possible because we are able to remove occlusion, and I will explain you at the end of the talk also why this is actually working. So here's another example for two people. This is again the original video footage with lots of garbage being tracked. So there's lots of false positives that are detected here, and this is the result of airborne optical sectioning, with again the bigger target being the static light source on the ground and the two targets that can be detected and pretty well tracked. So airborne optical sectioning, as I mentioned already, is a synthetic aperture sensing technique. Synthetic aperture sensing is very common in signal processing. All the time when you're dealing with a sensor whose sensing quality depends on its size. For example, a classical example would be a radio telescope. where the sensing quality of the telescope depends on the size of the telescope dish, with physical limitations on how large telescope dishes can be built. To break these limitations, basically what happens is you network multiple radio telescopes and computationally combine their signal to mimic a radio telescope with a really large virtual dish, which would physically be impossible to realize. So that's the idea of synthetic aperture sensing. Again, you do this with the goal to improve the sensing quality, and this idea is applied in many different fields, such as in radar. Synthetic aperture radar is a classical example of synthetic aperture sonar, in ultrasound, in microscopy, in LiDAR, and also in optical imaging. That is where we apply synthetic aperture sensing by capturing an unstructured light field using drones with conventional cameras. The images that we capture with the drone are computationally combined to what we call an integral image, which removes occlusion. So the basic principle of AOS is that we apply conventional drones with conventional imaging optics, but we capture multiple images throughout a large area over forest, and we then computationally combine these images. And that is relatively simple. So we register and average the single images here to an integral image. And that integral image is basically an image which mimics a very wide lens optic. So we simulate a camera with a really wide lens of several hundreds of meters in diameter, which physically, of course, isn't feasible, but computationally not. So that integral image, because it simulates wide lens optics, would support a very shallow depth of field, and because of that shallow depth of field, only objects located on the adjusted focal plane are clearly in focus and visible in the image, while all other objects that are not located on that focal plane are defocused so much that they disappear in the image signal. So that's the basic principle of airborne optical sectioning. Of course, you can explain it from a statistical point of view, why this works. You can imagine that a point on the ground, which might be invisible from a single perspective because it's occluded, might be visible from other perspectives. And since we combine multiple perspectives here in one image, we have a certain statistical chance to improve the visibility of that point on the ground. And we have also several publications that actually discuss the theoretical part and the mathematical part of airborne optical sectioning, explaining when it works and when it doesn't work. So in principle, the advantages of AOS is compared to alternative technologies such as LiDAR or synthetic aperture radar. It benefits from a high spatial resolution of digital cameras. It's real time, so there's the computational part of AOS is very simple, so there's no need for 3D reconstruction. There's no need for registering point clouds. So it's really real time. It's low cost because we apply very conventional hardware. It's just conventional cameras and drones. There's no special sensor involved here. And most importantly, it's independent of wavelength. So we can apply the same principle to near infrared, which is important for agriculture applications. We can apply it to far infrared, which is important for detecting, tracking living targets such as people or animal. And we can also apply it in the visible range, which has applications in agriculture, in archaeology, for example, or also, as you have seen before, in people tracking. So in this video, basically, or in this slide here, you will actually see the impact of AOS. Again, in a dummy example, basically what you see here is an image recorded by a drone with a camera that has an aperture or lens of a few millimeters in diameter. So the depth of field of this camera is very large, which means objects close to the drone and also objects further away are pretty well in focus. But with AOS, we simulate again a wide optics system, which gives you images with a really shallow depth of field, and by adjusting virtually the focal plane of the imaging system, we can optically slice through the occlusion volume, making sure that only those points that are located on the focal plane are clearly visible, while the rest is so much defocused that they disappear. So here you can actually see the slicing of a virtual focal plane from front to back, and you can even see the intersection of the focal plane with the ground where it's actually being located, and all of this is done computationally. So we carry out many field experiments with AOS. One of our first largest field experiment was done in 2020, and that was in the context of wildlife observation. You see here a wetland region at the Inn River, which is at the German-Austrian border. And this is a special place because it hosts one of the largest heron populations in Austria, and ornithologists are interested in counting the population, which you can imagine is very difficult to do when you're considering flying birds. So they try to count the population during nesting season, where they can expect that many birds are more stationary in their nests. The problem with that is you can't do it from the ground because the birds are high up in the trees, and you can't do it from the air because of occlusion, because during nesting season you have actually lots of vegetation, lots of leaves on the trees, so you basically are not able to detect the nests and the birds because of occlusion. So in this case we applied AOS to do the counting, to support the counting, because we are able to remove occlusion, and I would like to show you a short video on that project as well. So in this particular case, the classification of birds was done by the ornithologist manually by browsing through the data that we captured, and with that, we had another idea of maybe that becomes possible to do the classification of targets automatically using deep neural networks, and maybe we should look at other applications than bird counting, and that was when the idea was born to develop a fully autonomous drone for search and rescue. So the idea here is to find lost or injured people in forest. And occlusion is really a big problem for search and rescue teams that normally apply helicopters to find people. So again, here we are trying to find people. We hopefully are able to do this fully autonomously with a drone, and we need people classification, automatic people classification using deep learning. So the main hypothesis in this case was that if you apply a well-trained neural network for people classification, and we spent almost 2 years to record the data for the training data for training these networks. So if you apply a well-trained neural network to single images, and we are looking at thermal images here of different forest types, and you do classification, and you even integrate the classification of multiple single image detections later on, that this is significantly worse than integrating the images first and then carrying out the classification, and that's what AOS would support. So in this example, you can see results of the first idea. You capture normal images and you try to detect people in these images. The red boxes are false positives, the green boxes are true positives, the dashed boxes are ground truth labels, and the numbers that you can see are the confidence scores of the classifier. And as you see in this example, the classification does not work. We get average precision scores of less than 25% for many field experiments that we did. In total, in this case, we are able to detect only about 5,500 cases out of 10,700, but we also get more than 16,000 false positives, and that leads to the low average precision score of less than 25%. So in conclusion, person classification under strong occlusion conditions in a straightforward way does not work in a practical sense. That is very different if we integrate images first. So we use the same image data as for the single image classification, integrated as AOS does it for occlusion removal, and then classify, and then we end up with very high success rates. We end up with average precision scores of well over 90%. We are able to detect 53 out of 57 people that we were searching in forest, with only 2 false positives in total, and one of them was our institute dog. The reason why this works is, I guess, very obvious. In the first case, you see people only fractionally because of occlusion, and a deep neural network is simply not able to learn distinguishable features or features that distinguish people from other artifacts in forest, like heated forest ground, which appears in the thermal image. So if you see people only fractionally, then the classification will not make sense out of this information. But if you remove occlusion, obviously you can detect shape, you can learn about aspect ratio of people, and this is what a classifier would use for achieving these results. So this was the main finding in this Nature paper, that image integration, or integrating images first before classification, is significantly better than classifying in single images and then integrating the classification results in case of people classification under occlusion conditions. And of course, this would most likely also apply to other targets that we try to find. So with that, we tried to build our fully autonomous search and rescue drone. That means all computations had to be done on board and in real time. And for real time, we had to give up a bit of the imaging quality to achieve fast scanning flights. For example, we no longer scan in a 2D area, so our synthetic aperture is not 2D anymore, but it becomes 1D. We scan along a one-dimensional flight path of the drone. And instead of using precise computer vision based pose estimation, as you can see in the center image down here, which was the case for the Nature paper, we use error-prone GPS that we get in real time. And because of misregistration, because of the GPS error, we end up with misregistration, and that is what you see in the right image. So the difference between the science paper and the nature paper in visual quality is the difference between the two images that you see in the center and on the right. But in the science paper, we end up with doing this in real time, while in the nature paper, we do this offline after recording with all the processing power that was available, and computation time was several hours. So the main contribution in the science paper was to show that although we have this visual quality reduction because of lower sampling rates, because of error, a registration error due to GPS, the classification of a well-trained classifier does not suffer. So we still achieve the same classification rates as in the nature paper, simply because the networks learn the difference between person features and GPS errors, or imaging errors in general. And with that, since we do everything in real time on the drone, we can also allow the drone to make its own decision on how to fly, with the goal to find the person as quickly as possible. So it's not only the entire image integration being done on the drone and the classification, but also the dynamic path planning and dynamic sampling strategies are computed on the drone. So we really start with, say, an initial probability map that comes from the rescue team. They normally have a good idea where to search first and where to search later, so where the person is more likely being located, and where in other areas it is less likely to find the person. So we start with that and then fly. And this probability map dynamically changes during flight based on the confidence scores that the classifier gives us while doing person classification continuously during flight. So if the drone thinks it sees a person with a certain confidence, it will double check in that region to verify whether that was a false or true positive, and by doing that it changes its flight path. So the flight path is dynamically adapted with the goal to find the person as quickly and as reliably as possible. So in terms of classification, we have achieved a couple of improvements. So far, we could only fly with our drone with a speed of 1 meter per second. That was limited to the imaging speed of the camera that we used, which could only record 1 frame per second. We changed the imaging system to achieve a recording speed of 30 frames per second, and with that we can allow the drone to fly with a maximum speed of 10 meters per second. And we will also allow, or we can also allow, the integral images to overlap quite a bit. And because they overlap, we have now multiple chances to detect the same person in multiple integral images. So we run the classifier on multiple integral images with multiple chances to detect the same person. So we don't rely on a single detection in a single integral image anymore. And because we combine the classification results now in the integral images and not in the single images, we achieve even higher classification rates, because simply we have multiple chances to detect the person and not only one. So in future, we are currently working with companies that build long endurance drones that are not battery driven but use piston engines to achieve endurances of several hours. So these are the basis systems for our payload, for our AOS payload, which are realistic systems for search and rescue missions, for fully autonomous search and rescue mission beyond visual line of sight. So this is one activity that we are following at the moment with a company. And on the other hand, we also investigated EV-loss automatic systems, so basically off-the-shelf small drone systems that are very often used by police or firefighters to inspect local neighborhood region. They don't fly basically beyond visual line of sight. They are not autonomous, but they are automatic. So in this case, the drone itself is used as an imaging system, and AOS runs on a ground station. in this case, obviously, it's required to have a continuous network connection to the drone, which is not the case for fully autonomous BVLOS drones. Yeah, this is our latest prototype. The basis system is basically the same, but the payload is not. The problem with AOS so far is that because of the sequential sampling nature, we record the single image sequentially, obviously, since our prototypes have only a single camera on board. Simply because we sample sequentially, and that takes some time, even if you fly fast, we cannot deal with motion, because if we have motion, say of animals or people, during that sampling time, we end up with motion blur in the integral image, and that leads to false classifications and not being able to track. To overcome this is a first solution. To overcome this, we use a 10-meter long camera array. We built this from carbon fiber tubes. It carries 10 RGB cameras that are synchronized and capture in parallel, so we can at least record 10 samples in parallel to overcome the motion problem. And that was the system that was used to the tracking, or to the people tracking, that I showed you at the beginning. So it took us a couple of months to get this system flying. As you can imagine, it's not so easy to get such a system flying stable under all wind conditions without having it basically shake too much and get into certain frequencies in shaking that it does not fly stable anymore. So this we could achieve. We could achieve by changing the balancing of the system, and also we reprogrammed the drone controller to basically control or to balance the system much better. And instead of using a person classifier, deep neural network for classifying people, as I showed you before in thermal images, we now use color anomaly detection in RGB images. And the main finding here is very similar to the main finding in the Nature paper, and that is that color anomaly detection benefits a lot from image integration. You see in this example here, color anomaly detection being applied to single images. So of course there are thresholds that you can tweak to get certain results. So we tweak the thresholds here for the single images to get the best results out that were possible. So basically we try to make sure that the true positives, the green circle area here, are detected, and we minimize the false positives, which is the red circles here. So this is really the best results that you can get from these 10 single images in terms of color anomaly detection. And you see it's still not practical because you end up with so many false positives. The numbers are position values here, which is basically the ratio of true positives divided by true plus false positive. We count pixels here for true and false positives, not targets. At the bottom you can see the same 10 images, but integrated first and then applying anomaly detection, and you see that things change dramatically. We end up with 100% precision. We detect only true positive pixels, while there is not a single false positive pixel. So this is a case under bright light conditions. This is a case under dark light conditions. So after sunset, same situation. The reason why this works significantly better with AOS is that these color anomaly detection apply covariances to describe the background. And if you look at these covariance coefficients in the matrices that are used in the equations, these coefficients drop by a factor of 3 to 5 in integral images, and since the inverse matrix is multiplied, that leads to an increase in the anomaly scores. In simple words, the smoother the background, the better color anomaly detection works, and smoothing the background, the occlusion, is what AOS actually does. So this is a main finding, because color anomaly detection is very important for search and rescue systems that automatically analyze aerial images to find people. And this also enables the tracking that I explained to you before. The tracker that's being used is a very simple tracking implementation, but it works very stable simply because the color anomaly detection works very stable. This is it from my side. I thank you very much for your attention. If you're interested in all of this, we make everything publicly available on GitHub. So you find source code, you find all papers, including all the unpublished papers on archive. You find the data, and if you have any questions that I can't answer today, you can send me an email anytime. So thank you very much, and I wish you, of course, a successful challenge.